Welcome to the presentation on ethics in artificial intelligence. We will explore the critical intersection of artificial intelligence and ethical responsibility in the modern technological landscape. Here are some key ethical challenges in artificial intelligence. The first one is algorithmic bias, which involves addressing inherent biases in artificial intelligence systems that can perpetuate and amplify existing social inequalities through data selection and model design. Next are privacy concerns, which entail balancing the need for data collection and analysis with individual privacy rights and data protection regulations. Transparency is also important, ensuring artificial intelligence systems are explainable and their decision-making processes are transparent, which helps to build trust and accountability. And finally, accountability, which involves establishing clear lines of responsibility and liability for artificial intelligence-driven decisions and their consequences. Now let's discuss bias and fairness in artificial intelligence systems. Here is an example of potential bias in a hiring algorithm, where bias factors such as university name, zip code, and previous company can be included in the data. Therefore, we need fair evaluation metrics in order to calculate a fair score, excluding these bias factors. Historical data often reflects existing societal biases, leading to discriminatory patterns in artificial intelligence decision-making, which is known as training data bias. Underrepresentation of certain groups in training data can lead to poor performance and unfair outcomes for these populations, which is selection bias. Lastly, biased predictions can create self-fulfilling prophecies, reinforcing and amplifying existing inequalities, which is known as feedback loops. Let's examine privacy and data protection in artificial intelligence. The diagram illustrates the process of data collection, which requires consent, followed by data processing, data storage, data usage, and finally, data deletion. Data minimization means we should collect and process only the data that is absolutely necessary for the specific artificial intelligence system's functionality. We also need to ensure transparent communication about data collection and usage, obtaining explicit user consent, which is called informed consent. Finally, we must implement robust security measures to protect sensitive information from unauthorized access and breaches, also known as data security. Now, let's discuss transparency and explainability in artificial intelligence. LIME, which stands for Local Interpretable Model Agnostic Explanations, is a technique that explains the predictions of any machine learning classifier by approximating it locally with an interpretable model. SHAP, which stands for Shapley Additive Explanations, is a game-theoretic approach to explain the output of any machine learning model by calculating feature importance values for each prediction. Here is an example of model explanation using LIME. An explainer instance is created, and an explanation is generated to return feature importance. Artificial intelligence systems must be able to explain their decisions in human-understandable terms, especially in critical applications. Explainability builds trust with users and stakeholders, enables detection of potential biases, facilitates regulatory compliance, and supports continuous improvement. Let's discuss artificial intelligence safety and control measures. Runtime monitoring is implementing continuous monitoring systems to detect and prevent unsafe behaviors. For example, if the confidence score is less than a safety threshold, it can trigger a human review and log the safety concern. Performance boundaries include defined operational limits, automatic shutdown protocols, and error handling mechanisms. Validation testing consists of comprehensive testing frameworks to ensure system reliability and safety across various scenarios and edge cases. Human oversight involves regular human review of artificial intelligence decisions, clear escalation procedures, and intervention protocols. Here is an overview of the environmental impact of artificial intelligence. The annual energy consumption by data centers running artificial intelligence workloads is between 85 to 140 terawatt-hours. Training a single large language model can emit as much carbon dioxide as 5 cars in their lifetime. Sustainable solutions include implementing energy-efficient algorithms and hardware optimization techniques, powering data centers with renewable energy sources to reduce carbon footprint, and using model compression and knowledge distillation to reduce computational needs. Let's discuss the social impact and job displacement that can result from artificial intelligence. 85% of the jobs that will exist in 2030 haven't been invented yet. There will be an increased demand for digital literacy and artificial intelligence-related skills across industries. Education systems will need to adapt their curricula to prepare for an artificial intelligence-driven future. There will also be a need for support systems for workforce transitions and retraining programs. Here is a responsible artificial intelligence development framework. Technical excellence involves a robust architecture with fail-safes and error-handling mechanisms, quality assurance with comprehensive testing protocols and validation procedures, and performance monitoring with continuous monitoring and optimization of system performance. Ethical principles include fairness and inclusion to ensure equitable treatment and representation across all user groups, transparency to maintain clear communication about artificial intelligence capabilities and limitations, and privacy protection to safeguard user data and respect privacy rights. Finally, social responsibility includes minimizing resource consumption and environmental footprint, providing resources for skill development and career transitions, and active collaboration with stakeholders and community members. Let's review future considerations and best practices. Future-proofing strategies include implementing adaptive artificial intelligence systems that evolve with new ethical guidelines and societal needs, as well as designing scalable infrastructure that can grow and adapt to changing requirements and technologies. Best practices include conducting periodic assessments of artificial intelligence systems against established ethical frameworks, maintaining open dialogue with users, experts, and affected communities throughout development, and maintaining detailed documentation of decisions, processes, and potential impacts. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.